Hi, this is the presentation for the paper titled COLREGs-Informed RRT Star for Collision Avoidance of Marine Crafts. My name is Thomas Enevoldsen, and I'm a PhD student at the Automation and Control Group at the Technical University of Denmark. My co-authors are Christopher Reinartz and Roberto Galeazzi. The following slide is an overview of the presentation. Firstly, I will discuss the motivation and contribution of the paper, then the working assumptions, then provide an overview of the COLREGs, then I will introduce our method, the COLREGs-Informed RRT Star. I will then go into details with our proposed sampling scheme, then I will discuss the results, and finally the conclusion. In recent years, there has been an ever-increasing interest in the research on autonomous marine systems. Autonomy is expected to increase the operational efficiency and safety for the waterborne transport and logistics sectors. Merchant vessels will most likely receive a gradual adoption of the autonomous technologies, which will come in the form of a decision support system such as ANAS. A core functionality of such an ANAS system is the short horizon planner, which deals with deconflicting the collision scenarios that occur. This is expected to increase safety since human error remains one of the main sources of collision and grounding incidents at sea. The merchant fleet all have the existence of legacy systems in place, emphasizing that the task of planning a maneuver for collision avoidance must be decoupled from the task of motion control. The main contributions of the paper are as follows. The paper proposes two new sampling strategies, both of which are specialized for the marine domain. The proposed sampling strategies are applicable for sampling-based algorithms such as RRT Star. One of the critical and must-have components of any collision avoidance scheme for marine systems is the adherence to the rules of the road, also known as the COLREGs. The proposed sampling strategies directly encompass states that are compliant with these rules. Furthermore, the second of the two strategies leverages the idea of an informed set, allowing for a decreasing sampling region as the solution improves. The proposed planning scheme produces path length optimal and geometrically feasible deviations from the nominal path for single vessel encounters at open waters. The proposed method works under the following assumptions. The vessel considered as owned ship is assumed to have an underlying track control scheme in order to execute the computed sequence of waypoints. A geometrical constraint is imposed on the computed path to ensure that the sequence of waypoints is feasible with respect to the minimal turning radius of the vessel. By focusing on producing a sequence of feasible waypoints allows the track control scheme to deal with the system dynamics. It is also assumed that the target vessels have been successfully identified, possibly using a system such as radar and/or AIS, and that the identified target vessels maintains a constant course and speed. A safety barrier, also known as a comfort zone, is placed around the target vessel and is represented by an ellipse. Finally, all the encounters concern single vessels occurring at open waters. As previously mentioned, a must-have component for any collision avoidance system is the adherence to the COLREGs, which are the international regulations for preventing collisions at sea. The rules are defined for two vessels, both of which must be power-driven. Within research on collision avoidance schemes for marine crafts, the most commonly considered rules are Rule 8 and 13 to 17. The dashed vessel on the figure is known as the stand-on vessel in the left and rightmost encounters, with the orange vessel being the give-way vessel. The following slide provides details regarding the most common COLREGs. Rule 8 dictates that collision must be prevented at all costs and typically is applied when the give-way vessel is unresponsive, and therefore the stand-on vessel must take action. Rules 13 to 15 cover the three most basic encounter types. The overtaking scenario in Rule 13. The give-way vessel is allowed to overtake on both the port and starboard side of the stand-on vessel. During a head-on scenario in Rule 14, both vessels must perform maneuvers towards starboard. And during a crossing, in Rule 15, the give-way vessel must give way performing a maneuver towards starboard. In Rules 16 and 17, the overall behavior of the stand-on and give-way vessels is dictated. Human navigators and automatic collision avoidance schemes primarily utilize CPA and TCPA as metrics for determining whether or not an evasive action must be taken. The closest point of approach, or CPA, is the distance of which two vessels will be at when they are at their closest. Whenever this distance is less than some limit, an evasive action must be taken. TCPA, or time to closest point of approach, is the time until CPA, which is typically used for initiating the planning phase or as a limit for when a maneuver must be executed. The main output from the presented work is what we call the COLREGs-Informed RRT star, which is built on a marine-oriented RRT star algorithm together with the proposed sampling schemes. By investigating the COLREGs rules 13 to 15, we identified that they could all be represented by some sort of annulus. The center region of the annulus, shaded by red, ensures that no samples are computed that violate the CPA limits. For a crossing scenario in Rule 15, over half of all samples would be rejected due to proposing a non-compliant deviation towards the port side. States which are strictly COLREGs compliant are encompassed for both the head-on and crossing scenario within the region of a half annulus, with the overtaking allowing both a port or starboard maneuver, therefore represented by an annulus. The paper also introduces an informed annulus-like sampling space. Informed RRT star, introduced by Gamel et al., consists of an ellipse which major and minor axes are scaled by the minimal solution between the goal and start positions and the current best found solution. The informed set decreases the sampling space in order to increase the probability of improving the solution cost. To summarize, the COLREGs-informed set reduces the region of interest to only encompass the states which are COLREGs compliant, with the region decreasing in size as the solution improves, similar to the original informed RRT star. The main objective is to produce a uniform sampling strategy of the proposed annulus-shaped region. Sampling a point in the northeast plane can be formulated in terms of a radius r and an angle theta. The angle theta is represented as the uniformly distributed random variable between theta min and theta max. The radius, however, requires some additional derivation. The PDF for the annulus is given as follows, which consists of the areas of the inner and outer circles. By obtaining the CDF and inverting it, it is possible to obtain the radius by using the uniformly distributed random variable u to compute r. The figure to the right showcases the quantities r min and r max, with r min being dictated by the chosen CPA limit. The concept of the elliptical informed subset is further extended to exclude the inner region such that it can represent an annulus-like subset that can decrease as the solution improves. The ellipse is represented by an angle theta, the angle-dependent radius r max, and an inner circle governed by radius r min. The major and minor axis of this ellipse is computed similarly to those presented in the original work on the informed RRT star. The resulting PDF is then given on the slide with its accompanying CDF. No exact closed-form solution exists for computing the angle, and therefore the inverse must be solved using a routine such as Newton-Raphson. The angle theta is then computed by setting the CDF equal to the uniformly distributed random variable u and solving it iteratively. Once the angle has been obtained, r max can be computed using the first equation, and the radius can be sampled in a similar fashion to the half annulus. In order to utilize the proposed informed sampling scheme, an initial solution must be obtained. However, immediately switching between the two sampling schemes may provide a disadvantage. If the initial solution has a very long path length, the area of the informed set may be much larger than the half annulus. Therefore, a switching condition is computed offline in order to switch between the sampling strategies when sampling the informed set provides more value than sampling the half annulus. The figure compares various sampling regions discussed throughout our paper, and also the schemes we compare against. The most commonly utilized scheme is a rectangular sampling space, since producing uniformly distributed points is trivial, and rejection sampling is so effective. The full ellipse represents the original informed subset, which focuses the uniform sampling to regions which have a high probability of improving the solution cost. However, both the rectangular space and the regular informed space would spend a significant amount of effort sampling points outside the COLREGs compliant region. On this figure, all area above the nominal trajectory is deemed to be non-compliant with the COLREGs. The figure also demonstrates that the scheme samples in the half annulus before switching to the elliptical annulus and therefore focusing the search. The proposed annulus and elliptical annulus sampling strategies are compared to a rectangular region and also the rectangular region together with the regular informed sampling strategy. The results show that even with the added complexities of the proposed sampling schemes, the elliptical annulus and the annulus sampling strategies converge to the optimal cost faster than the two baselines. The rightmost figure visualizes the tree development by the RRT star algorithm when subjected to the combined sampling strategy of the half annulus and elliptical half annulus. In order to conclude, this paper presented the concept of the COLREGs-Informed RRT star. The two sampling strategies directly encode the COLREGs, or the maritime rules of the road. The proposed strategies sample the regions uniformly in order to preserve the properties of optimality within algorithms such as RRT star. The COLREGs-Informed RRT star was compared against the current state of the art and demonstrated a significant performance increase. The planning routines computes path length optimal deviations for single vessel encounters at open waters. Thank you for listening. I would like to acknowledge the support from my co-authors, Christopher Reinartz and Roberto Galeazzi, as well as the Shipping Lab project and the other project sponsors.